channels are prone to errors and loss. In this case, we will assume that our channel can lose the packet also. In the previous case, we only consider about corruption. In this situation, can be handled with checksum, sequence number, acknowledgements, and retransmission, which was mentioned in previous technique or previous version of RDT. In this case, we will wait for a reasonable of time for ACK. That means acknowledgement. We will wait for that time so that after that the sender will assume that the receiver did not receive the packet or there are problems. The sender will retransmit the packet. And if the packet or the ACK just delayed, not lost, in that case, the retransmission will be duplicate. That means the ACK was actually the actual packet was received correctly, so that will be duplicated. But the previous version of RDT already handles how to handle the duplicate packet, and this is done by sequence number. The receiver must specify the sequence number at the time of sending the packet of ACK, because that's how actually the sender will understand the whether the packet was received or not. And as we have to wait for a reasonable amount of time, that means whether a packet is received or not. If to check that, we have to wait for a reasonable amount of time. We need a countdown timer. The finite state machine of RDT sender for version number 3 is including the timer portion. Whenever you send the data, you also start the timer, and at the time and move to the waiting for acknowledgement from waiting from call from above. And while you actually see that the packet is corrupted, you can actually corrupted or something happens, so you just wait for the ACK again. But in case of timer, you actually resend the packet and wait for the resend the packet and start the timer. And whenever you received correctly, that is the condition or event presented here. So whenever you received correctly, you will move to this portion called for the sequence number 1 you are waiting. And in this case also, you will start the timer and wait for the acknowledgement. Whenever the timer occurred, it will retransmit, or if it is actually okay, then it will move to the 0 number waiting state. Or if it is not actually received correctly, then it will wait that whether the packet will be received correctly or not. Let's see the RDT3 for portion in action. So in the first case, we have packet 0 received normally. So we are observing where no loss happened. So it just receive packet 0. It will acknowledge ACK 0 number, and it will be received by the ACK 0 number. And after that, PKT packet 1 will be forwarded or sent out. And again, packet 1 received, then ACK 1 will be sent out, and similar happen for packet 0 again. Okay, so that is no loss. If the packet is lost for some reason, assume that here our packet number 1 is lost, that means receiver did not receive it, so it will not actually send out any acknowledgement packet. So in this portion, actually it will see that after a timeout, after a period of time, the timeout will occur, and packet 1 has to resend again, and the packet 1 will be received by the packet 1 will be received by the receiver, and the same thing will go on smoothly. So we see the problem that if the packet is lost, in that case, the sender has to wait for the that reasonable amount of time, that is the timeout time, and it is it is actually written hard coded to the to the protocol. So already it is decided. Okay, so for understanding, we are actually saying a reasonable amount of time. Now we will actually assume that our packet was received normally, but the acknowledgement was lost. So in this case also, the sender will see the timeout because ACK was not received correctly. So after the timeout, it will actually retransmit the packet number one again, because it will assume that my packet might not be received by the receiver. And we understand that this will be a duplicate packet, but it will be actually it has no problem. It will just reject the previous case, and it will actually send out the packet number one again. Okay? Sorry, acknowledgement one again, so that the sender will send the packet number 0. In this case, actually, again, here we will assume that premature timeout occurred. That means our timeout, uh, though the packet was actually received normally, and sender receiver also sent out the acknowledgement, but before even reaching it to the receiver, the timeout occurred. So there is premature timeout. In that case also, sender will assume that the packet was lost, and it will retransmit again. Let's see the performance of RDT 3.0. In this case, we are assuming that our link is 1 Gbps, so it is bit, and we have a 15 millisecond propagation delay, and the size of the packet is 8,000. Let's see what are the cases. We will actually first calculate our transmission delay. So the transmission delay is kind of, you have a sender and a receiver. If you assume a pipe of water, here the cross section actually indicates that how much water you can take in a single unit time, and the velocity of the speed or the velocity of water in this direction actually indicates that what will be the propagation delay. That means how much time it is required from a portion of water from this point to go to this point. So that is the propagation delay. So the transmission delay, it will be calculated by L by R. That means the first one is the packet size, and the second one is the actually the link size. Okay. So here actually packet size is 8,000, and 10 to a 9 beat per second is the link speed. So it will take 8 microsecond for 8,000 bit data. 8,000 bit means 1 kilobyte data. 1 kilobyte data from 1 kilobyte data to be on the link is 8 microsecond. We are assuming 15 millisecond propagation delay. So in that case, as it is 15 millisecond propagation delay, there is an average time, and we are assuming that it will go from S to receiver and receiver to S. So that will take 15 into 2, 30 milliseconds of time, and which is represented by RTT, or round trip time. Okay. So 30 millisecond time will be taken for propagation for round trip, 1 kilobyte data, and 30 microsecond 30 milliseconds is actually uh, for every 30 millisecond you will actually send out 1 kilobyte of packet. So for sending out 1 kilobyte of packet, actually so the throughput becomes 33 kilobyte per second. Okay, because you see 30 millisecond, if you in 1 second how much it is, so it is 33 kilobit per second. So let's see the network protocol. Here we can assume that the network protocol actually limits the use of physical resources. So you see, even after you got a 1 Gbps link, you have this less amount of throughput. So here is another, here is the previous calculation. Here from these actually we can understand that RTT plus L by R. So this is the total time for a packet to wait for a packet of 30 1 kilobyte to from one place to another, from sender to receiver. So this is the time required, 30.008. This is millisecond. So if you convert it to second, so it is 0.03008 second. it will actually send out 8,000 bits. So in 1 second you will actually get 267 kilobit per second. So that is that is our uh, throughput. So in this case, actually, we can see from the diagram also the time to send out the actual data is very less, but the waiting time, that means RTT, where the sender is waiting for the acknowledgement, is very high compared to the sending data. So this protocol actually makes the link idle. So you are actually underutilizing the physical resources. So in this situation, actually, how can we improve our protocol? The idea is pipelining, and the what is pipelining? Uh, Instead of sending one packet, we will allow multiple packets to send out at the same time without getting acknowledgement from the receiver side. So in this case, actually, we need to increase the range of the sequence number. In the previous case, we have only two sequence numbers, 0 and 1. Now we need to have more sequence number from 0 to the window size. Okay. So two generic form of pipeline protocol is go back in ARQ and selective repeat ARQ. We will see these two protocol here. One important factor is that you have to buffer at sender and or in the receiver side, because you are actually getting multiple data packet at the same time you are sending out. So you have to buffer this packet. So pipelining will increase the utilization in such a way that in the previous case you will send out only one packet. Now we are assume that you want to send out three packets at the same time, and we are not waiting for any acknowledgement. Here the RTT time, that means round trip time, will be calculated, where that after that the retransmission will occur. So it will be calculated from the first packet. So from the oldest packet, the timer will start, and it will actually after this timer period, the all the packets from the oldest packet will be retransmitted. So you see that ACK receives send next packet RTTL by R. So here the ACK will be actually received here, and after that it will understand that I can actually send out the next three packets. Okay, so this sending out three packet in pipelining will increase the utilization by factor of 3. So if you just see the calculation in the previous case, you just multiplying 3 into L by R, because this is the data packet you are sending out in this period of time, and this is the total time required. So here the factor is the utilization increased by this amount of by factor 3. So we will actually see the overview of go back in ARQ and selective repeat ARQ, where these two protocol actually follow the pipeline technique. In case of go back in ARQ, as the name suggests, it will actually send out n number of unacknowledgement packet to the senders to the receiver side without caring about the acknowledgement. And in the receiver side, receiver only sends out cumulative acknowledgement, as in that it receives one packet, and after that it receives another packet. So the second packet, it will actually, the first packet was 0 number sequence, second packet is 1 number sequence. After receiving 1 number sequence, it will actually send out at ACK1. But assume that after ACK1, after 1 number sequence, the 2 number packet is missing, and after that 3 number packet and 4 number packet is again comes up from the point of receiver. So what happens is 0 is received, but 1 is received, 2 is missing, then 3 is received, and 4 is received. So whenever 2 is missing, whenever there is a gap, while the packet 3 will be received by the receiver, it will actually remove that actually packet 3 and remove the packet 4. Why? Because it cannot acknowledge 3 or 4. whenever we say is cumulative acknowledgement, it means, it implies that whenever you say ACK4, it implies that all the packets before 4 is also acknowledged by this packet. So as the packet number 2 is missing, so as the packet number 2 is not actually missing, so you cannot actually so you cannot receive 3 and 4 packet. Okay, third and fourth packet you cannot actually accept it. So sender has a timer for the oldest account acknowledgement packet, and when the timer expires, retransmits all the unacknowledgement packets. So we got that point also from the previous discussion. In case of selective repeat ARQ, the idea of go back in ARQ, we see that whenever you have missing in middle, one packet is missing, the next packet will not be accepted. That means that the go back in ARQ follow the in order acceptance. So in some, if you miss one packet, if the receiver miss one packet, then it will not, it will wait for that packet only. Whenever that packet shows up again, and after that it will receive again. So it will not actually accept any packet out of order. But in case of select, so that is a problem. You see that whenever it actually it doesn't actually get one packet, but it gets 5 packet after that, and all of these 5 packet will not be accepted. So you see the utilization again decreases, isn't it? So comparing to that, so to solving that problem, another idea was generated called selective repeat ARQ. In this case, they will send out individual acknowledgement for each packet. So in some book, you will see that negative acknowledgement is used. That means if a packet is missing, that packet's negative acknowledgement will be sent out. And for the cumulative ACK will be used also. So there will be no problem. Whenever a packet is missing, then negative acknowledgement is sent out, and all other packet might be actually comes out of order. Still, it will be received by the receiver, and there will be no acknowledgement for those. Whenever for the negative acknowledgement, whenever the sender gets the negative acknowledgement, it will retransmit again and do those things. So in this slide and in this book, we will follow the idea where negative acknowledgement will not be used. Rather, the timeout will be used to find out whether a packet is missing or not. So the sender side will assume that sender sends out 0, 1, 2, 3, and 0 number is acknowledged. That means received by the receiver and sent out. One number was received. One number was missed. Okay, one number is missed in the receiver side, and after that 2 number was received, 3 number is received. So the receiver will actually acknowledge only ACK 0, but after 1 it will actually wait for some time, and whenever there is whenever the timeout will occur, in the meantime 2 and 3 is already received. So whenever 1 is actually whenever the sender's timeout for 1 is expires, it will retransmit and you will get the packet 1 again. So we can actually understand that the selective repeat ARQ should perform better than the go back in ARQ. So sender maintains a timer for each of the unacknowledgement packet, because it will actually it will acknowledge the packet individually. That's why it will have a individual acknowledgement. Okay, so sender maintains timer for each acknowledgement. So that's what is written. So we understand that here go back NARQ will require more sequence number in the packet header, because you have to identify uniquely that these are the packets. If you don't identify uniquely, it might be a case that the receiver side will misidentified some packet to be misidentified some packet where those packets were duplicate, but they will assume that that is a new packet and actually accept it. So that's a problem, and you have to increase the sequence number range so that those problem will not occur. So this sequence number is selected based on the window size also, or there is a relation between the sequence number and the window size. So what is a window? Here window is actually representing a portion of the sending data packet. Here the sender window is representing the sending portion, where you have some packets those were transmitted already but yet acknowledgement is not received. There are some packets where it will be transmitted without getting any acknowledgement also. That means it will not actually wait for any acknowledgement. It can be sent out. So this is the window size and this value is the n. So the go back n ARQ, that n is this one. So it represents that among this window you can actually send out anything. And the previous before the window in the left hand side you see green color boxes representing that those packet were actually received by the receiver and acknowledgement is also received. So we have to actually send out the new one. So whenever this actually two packet will be received by the sender, whenever the acknowledgement of these two packet will be received by the sender, the window will shift to right. So the starting of the window will start from here, and these two thing will be colored to green color, and it will include more two bits this one in this way, more two packets in this way. So this is also known as sliding window because it has the property of sliding from left to right. It is slided to include more data packet, which packets can be sent out without getting any acknowledgement. So I think you understand the idea of the window. So this is the extended FSM, where finite sequence actually machine, where finite state machine, not sequence machine, finite state machine, where ACK is actually where the receiver side is shown here. So in the receiver side, it also check with the received packet with the expected sequence number. You see that in the previous case it was not actually doing that, because in case of the previous case was wait stop and wait ARQ, where only two packet, where you wrote FSM, where for 0 and 1 you just hard coded it. But in this case you have to know what is the expected number. It can be 0, 1, 2, 3, 4. The size of the n can be increased. So you have to keep track of expected sequence number, and which is also done here. So whenever you receive the packet correctly, you send it out to the upper layer, as well as you increase the expected sequence number. So after receiving 0, your expected sequence number is 1. So in this way actually you actually keep track of the ACK, the expected sequence number. There is actually another, you can say another modification might be required, where expected sequence number will be will not be only the addition, but it is modulo addition. That means after 7, if the size is up 3 bit, that means 0 to 7 is the sequence number range. Then after 7, one addition will give you the expected sequence number to 0. So you can say it is modulo 7 actually addition. Okay. Now what about the out of order packet? In case of out of order packet, it will discard, it will not buffer for the GBN, go back in ARQ, and it will re-acknowledge the packet with higher in order sequence number. So this is in action. If you just go through it, you will understand very easily. So the blue color is the sliding window. Here the windows n value is given is equals to 4, and your sequence number is 0 to 8. Actually in some situation you will see that the sequence number is kind of actually using bits, so it might be 0 to 7 also. Okay, so 8 data. So and your window size will be 4. Okay, so in case of go back in ARQ, you see that packet 0 and 1 is sent out, but packet 2 was actually lost at the transmission. So you see that there is no change up to this 4 transmission, because it is not waiting for the acknowledgement. And after sending out this 4, that means this is the window, the whole window is sent out. It will wait, and in the meantime it will receive packet 4 and packet 5. And after receiving sorry, let me clarify again. It will receive the acknowledgement 0 and acknowledgement 1. Whenever it receives the acknowledgement 0 and acknowledgement 1, the sliding window moves to the right. So for that, it can again send out number 4 and send out number 5. So that's why packet number 4 and packet number is 5 was sent out. So you see that even after that, as the packet is lost in the second packet is lost, all the other packet is rejected, okay, or discarded by the receiver. And whenever and we are keeping track of the oldest the timer for the oldest packet. So here the oldest packet is packet 0, sorry, not packet 0, the second packet, because second packet was lost, and that is in the window. So second packet timer is timeout. And we remember that at the time of go back NARQ, if the timer ends for the second one packet oldest timer, the oldest timer timeout happen, then all the packets in the window will be retransmitted again. So and this makes sense, because if the first packet was not received correctly, all other out of order packet will not be received by the receiver because of the protocol, because out of order packet will not be buffered by the protocol, so it will actually reject it. So we have to retransmit all the packets from that packet too. Okay. In case of selective repeat ARQ, receiver individually acknowledges all the correctly received packets, because and it will also buffer the packets out of order also, because it receives the packet out of it might the receiver might receive a packet out of order, so it will buffer these packets so that eventually in order delivery in later on it can give an in order delivery to the upper layer. Because in case of giving it to the upper layer in out of order delivery, there might be a chance of actually making mistakes by the upper layer. So it will buffer the data that is received, but there is a gap in between, that means out of order packet, so they will be buffered to send out to the upper layer. So senders only resend the packet where it doesn't get any acknowledgement. That means as the acknowledgement are not cumulative in case of selective repeat ARQ, so it accepts the data packet, and it sees that which acknowledgement was not received by the receiver sender, then it will send that it will actually an individual timer is also there. So for that, whenever that timer actually whenever that timer is actually timeout occur, then that packet will be retransmitted. So here the sender window, there will be n consecutive sequence numbers, and this sequence number, it limits the sequence number that can be sent and as an unacknowledgement packets. Similar to the previous go back NARQ, we can see the figure. Here actually an interesting situation happens. Here actually you have 3 categories of data in a window. One category of data that is actually you see that it doesn't get any acknowledgement yet, but it is sent out. The green color represent that it is sent out and it is acknowledged. So you see that there is unordered, sorry, out of order packet that was there, that is received by the receiver, or something else is happening. That means the sender actually can confirm these 2 packets, these 2 green color packet that is received by not others. So the timer of this one and this one, the sender is waiting for the timeout, and whenever the timeout occurs, this yellow colors packet will be retransmitted again. Okay. So in the receiver side, what is happening, though in the sender side, this yellow color packet represent that this packet was not received, but we can see the situation that this is received by the receiver. So we can assume that why this is yellow color, because they are actually the acknowledgement was not received by the received by the sender. So here the acknowledgement was received by so that's why, though it was actually received, but sender doesn't know about it. But in the case of receiver side window, actually it didn't receive the ash color one. So this is also represented in the sender side, that that was not received, and after that this one and this one was received, this one was not received, and this one is received again. So what will happen? The timer will occur. This packet will be retransmitted. This yellow color packet will be retransmitted one by one. But as this will be duplicate in this receiver side, it will be discarded, and only that packet which was actually out of order will be accepted. Okay, so that is the idea for the selective repeat ARQ, and let's see the diagram. So let's see the diagram directly. So there are actually some summary of the sender and receiver side. So in the sender side, you have actually n equals to 4 again. From 0 to 4, the packet is sent out. So again, similar situation, the packet 2 was lost. But whenever packet 2 was lost, so it sends out acknowledgement 1, and 2 was lost. It receives packet 3 and it is buffered. So it will not be sent out to the upper layer, it will be buffered by the given layer. Okay, and it will also send out acknowledgement 3. But this acknowledgement is not cumulative acknowledgement, so it is just saying that the third packet is received correctly. Okay, so if the receiver receives this acknowledgement here, and whenever it receives this one, so it is slided to this direction, because 0 and 1 is received, so it is slided this direction, and packet 4 and 5 is sent out. But acknowledgement 3 is, or it is recorded that acknowledgement 3, we got the acknowledgement 3, but I cannot slide the window, because the packet number 2 was not acknowledged yet, and here the packet 2 timeout will occur, and it will retransmit the packet 2 again. So only packet 2, not 3, because 3 is acknowledged. So it understands that the packet 3 was received correctly, and after the retransmission, it also got to know that packet 4 and packet 5 was received. So because of this acknowledgement, so it doesn't actually retransmit all the packet, rather only the packet that's timeout would happen, that was retransmitted. Okay, so this is the selective repeat ARQ. So there is a dilemma. So in this case, actually, sender window after receipt, and this is after receipt, is showing that window size is assumed as 3. So you have sequence number 0, 1, 2, 3, and window size is 3. So here actually the problem is the window size was actually assumed very large compared to the sequence number. So we already know that there should be a relationship between window size and sequence number. So packet 0 was sent out, packet 1 is sent out, packet 2 is sent out. So 0, 1, 2, 3 is there, and then 2, 3, 0, and 3, 0, 1. So this is slided. Assume that packet 3 was lost and packet 0 is sent out again. So here it will accept, sorry, packet 0 will send out. This packet 0 is which one? This one is the next 0 number packet, and will accept the packet of the sequence 0. There is no problem, because there is no issue. Now let's see the problematic situation. Here the packet 0, 1, and 2 is sent out, but all of the acknowledgement is lost. In the previous case, the packet itself lost, there is no problem. But if the packet, the acknowledgement is lost but the packet was received by the receiver successfully, there will be situation where it will assume that, okay, the timeout happened, let's retransmit 0 again. So in this case, this 0 is not this 0. This is the first 0. So this one. So the receiver is actually will get again a sequence number of packet 0, and it will assume that, okay, I get the new packet 0, but it is not the new packet 0, it is rather a old packet 0. So this is the problem between the window size and the sequence number. because the window size was actually assumed very large than the sequence number. So you have to assume that the we are actually seeing the both party, but here the receiver can see the sender side or sender behavior. So something very wrong will go on at this time. So how to see the actually handle this situation? Duplicate the data except as new, and what is the there should be a relationship between the sequence number and window size. So to problem have a number to B, and your task will be to find out what is the relationship between the window size and sequence number. So that will be end of today's topic. Thank you. You should go and give the attendance. I will in the section A, just give the attendance and you can leave. Thank you. Assalamu alaikum. Do you have any question? So thank you for attending, Tanvir, Kaji Shahab, and Jannatul Firdaus.
স্যার অ্যাটেন্ডেন্স দেয়া যাচ্ছে